This week we're going to talk some about power generation and distribution and energy. We'll be talking more about generators in another learning module, but we'll introduce some of the basic concepts this week. This shows some very early power stations. They were originally small, but that was okay because the demand was small. Obviously as time goes by, more and more machinery, electrical machinery and devices are in use, so the demand increases and larger stations need to be built to provide that demand. Generally, what you're going to have is at the heart of a power plant, power station, is a generator. And a generator, as we have talked about a little bit and as you're familiar with to some extent, and as we'll learn more about as we go through this course, is a device that typically rotates, and by doing so is moving conductors through magnetic lines of flux. And we know from Faraday's law of generation and induction that whenever you have a cutting of magnetic lines of flux and conductors, some sort of relative motion that causes those lines to be cut, that causes the electrons to move inside that conductor, and we have current flowing and voltages created as a difference of charge from one place to another occurs. Here we have an electrical circuit, and just looking at it, you don't see a battery or a power source, but you see this coil. And one end of the coil is attached to this lamp, and the other end of the coil is also attached to the lamp. And we've got a voltmeter attached in parallel that we can measure any voltage across this lamp. So if this were a power source, we could say that it would leave on one of these wires, enter this contact, flow through the filament, and exit on this contact, and we would have a complete circuit. Now, here I have a magnet, and I'm going to place it here and turn on the field lines. Now you notice that this magnet sitting inside of this coil has no effect on the circuit. There's no voltage, there's no indication of current flowing in the bulb. Being in the presence of magnetic flux is not enough to induce a voltage. In order to get electrons to move, to create that voltage and to create current flow, I have to have cutting of those lines of flux. Now either I can move the magnet and cause those lines of flux to cut across the coil, or I can move the coil and leave the magnet stationary, but in any case, that relative motion causes those lines of flux to cut across that conductor, that coil, and that causes the electrons to move inside of the conductor. So we'll start out here, and you'll see that as I move this back and forth, I see the effects of the motion of current. If I move it a little bit, I'm not seeing anything because I'm not really cutting any of these coils with the flux. I've got some on the inside, some on the outside, but none's being cut. I actually have to start crossing those lines before the electrons will move. Notice that one direction, the voltage goes one direction, and in the opposite direction, the voltage polarity is also reversed. So this is, and the current obviously is also reversing. So this is an alternating current situation. Notice that the slower I go, the less effect it has, but the faster I go, the more current can flow. So here's another arrangement that's similar. Here's my coil again. It's attached to a load. And here's my magnet. In this case, I'm moving the magnet around in a circle. So this is much like what a generator would be. So to get this thing in motion, I've got a prime mover. We'll use this stream of water to turn a water wheel, and attached to it is a magnet. And you'll see the effect that that magnetic field has on the electrons in the conductor. Notice that they are flowing one direction and then they flow the other direction. The current direction is alternating, hence alternating current. And the work that's being done is being done whether the electrons are flowing through the load one direction or the other. Now, we see that the output is not very high because if you remember Faraday's law, the speed of the cutting of those lines of flux affects the output of the generator. So let's increase the speed of the generator, and we see an increase in the output as a consequence. And as we speed it up even more, the output of the generator increases until we get to the max speed here at 100 RPM. Now you see that the intensity of the load is changing as I, for an instant, stop direction as I switch between forward and reverse. But this isn't noticeable at the types of frequencies that we experience in our house. So this is running at 100 RPM, and our house current is at a frequency of 60 hertz. That means 60 times per second. So if you do the math, in order for a generator to turn to create this effect happening 60 times a second, it would have to turn 3,600 RPM. So at that speed, which is 36 times faster than what we're seeing here, at 3,600 RPM, you would not be able to notice this change in intensity. It would be happening so quickly that you wouldn't be able to detect it. And in fact, the bulb really wouldn't be able to cool down to the extent that you would notice it, even if you could catch a change occurring that rapidly. And in actuality, we can create generators that can run at that speed or less and still increase the frequency output by using multiple poles in that generator. So the effects of this brightening and dimming that you're seeing here, variation in the load output, would not be evidenced in most practical applications with a generator. So the generator typically is rotated by some device. Whatever that device is considered to be the prime mover. So the prime mover in this example is a turbine, which is a set of blades. It's connected to a shaft to the generator itself. So the idea in any power generating station like this is that you turn the turbine with something that's going to flow through those blades. In this case, it's water. So I have dammed up a river and I have built up this pressure from as the weight of this water increases as it backs up, and I can let that water flow through here, turning those blades of the turbine and thereby turning the generator and cutting those lines of flux. And then that's sent off to distribution systems. In this particular case, rather than using water in the hydroelectric plant that we just looked at, here I'm using steam to drive my turbine. I still have a generator that goes out to my distribution network, but the prime mover in this particular case is a steam turbine instead of a water turbine. And I've got a coal supply coming in off barges typically, because we build these a lot of times on the river because of this supply of coal coming by barge. Run it in, we grind it up into a very fine dust. In fact, it's a lot like graphite, and it is injected with, like, it's so fine that you just inject it into the flame, and that flame heats water, these tubes of water that are in this boiler, and that steam that's produced is fed through the turbine. The turbine blades are turned by this steam, and the shaft that connects the turbine to the generator allows this rotation to rotate the windings inside the generator. Note that the steam is very hot as it goes through here, and in some cases we cool that steam, and those cooling towers that you see at power stations is for that purpose. Here is another steam driven turbine, but in this case, rather than using fossil fuel, burning fossil fuel like coal or oil or natural gas, here I'm using radioactive piles to cause reactions that heat up water. Another example, you see that my nuclear reactor here causes this heating. I've got a pump here that moves water through, and that in turn, there's a heat exchange here in this steam generator where this water that's flowing in is converted to steam, driving the turbine. Shaft drives the generator, distribution out to the electrical loads. Looking inside of a wind turbine, here I still have a turbine, but it's these big blades here, right? That's powered by the motion of the wind. And still have a generator on the output here, and this would go out to a distribution network. A couple of things that we take a look at. This device here is a gearbox, and it's either a constant speed through clutches or some sort of variable transmission type of arrangement, so that the generator can run at a set frequency so that my electrical current is 60 cycles per second. Another way we can adjust the speed is by adjusting the pitch on these blades. And there's a motor here, and these blades are able to rotate, and these gears will cause that pitch to change, thereby affecting the speed. Another thing that we can do is we can rotate this whole assembly here on this shaft. There's a little motor here that's like a rack and pinion type of arrangement that I can move this so that it's facing the wind for optimum efficiency. Another cutaway, you see the blades of a turbine, whether it's being driven by steam or water, and rotates, shaft driven. My windings, my conductors are in here, the magnetic fields are out here, and those conductors cutting through those magnetic fields causes the voltage to be induced. Here's a bank of generators. I think there's 1, 2, 3, 4, 5, 6 of them. Here's kind of a close-up, the shaft coming from the turbine and going into the rotor, and the windings are all up in here. And this is still a relatively small generator. Now, in transmitting electricity, we use transformers. We'll learn more about transformers. We talked a little bit about them. We know there's step-up and step-down transformers, but we use those in the distribution and transmission of electrical energy. So typically what we do is we generate a voltage at the power station and feed that directly into a step-up transformer. And we'll transmit this over long distances to avoid power losses, very high voltage. And we'll talk more about that too in a couple weeks. So I'm stepping up the generated voltage to a high voltage, low current, so that it can be transmitted over long distances without power losses in the line. There are some customers that will take these high voltages. Mostly they're other power companies that are going to market, kind of distribute and sell the power that's being generated over here, and they'll send it out to their customers. Otherwise, we send it on to small cities and towns. But because this voltage is so high, we don't want it going through the cities and towns at that level. So they have these substations that are sitting around that you've seen around. These are all transformers inside of those substations. It steps it down to a much safer voltage. And now we can distribute it to some customers who will use very high voltages, mostly industrial applications. Some use some a little bit smaller. And then near our home, we're going to have a final step down transformer sitting on the pole that will take it down to like 120 volts and 240 volts. Another example, we see here. Now, when I mentioned that we step this up to avoid power losses in the lines, take an example of this. Let's say that I've got a customer that needs 10,000 watts, 10 kilowatts. And if we were to send that at 100 volts, that would mean that there would be 100 amps in these lines. 100 amps in these lines. Well, that takes some big wires, so there's an expense there. But think about the power loss. The power that's created in any type of device is I squared times R. So even if R is very low in these lines, 100 squared, we're talking about a lot of watts, a lot of power that's being wasted as heat in these lines. So if we use a transformer and I still send out 10 kilowatts, but in this case I'm going to send it at 10,000 volts because I've used a transformer, now my current's only 1 amp. So you can see that the power losses in those lines are much lower, and the conductors required to carry the lower current are much less expensive. Here's another representation. Now, ratings have power, devices have power. Now, devices have power ratings, and typically they're listed on what they call the nameplate data. And what is being consumed is not the same as what's being converted into usable energy. So in this particular device, it's rated 120 volts and 1050 watts. So if we divided 120 into 1050, we'd know how much current it draws. But it doesn't put out that much. There are inefficiencies in any system. So in this particular case, what you're wanting to get out of this in terms of power is not the same as going in because of those losses. The power rating of a generator, we see it's 12 volts. It's a 60 amp generator, so 12 times 60 is 720 watts. Sometimes things will be rated just in the watts, but you'll typically know the voltage of that device and you can calculate current. If you're only given voltage and the current, then you'll be able to calculate the wattage. Now what they're wanting to know here, what's the power that's being dissipated in this heater? It's got a heating element. Maybe it's inside of a hot water tank, maybe it's a baseboard heater, but in any case, it's 120 volts. It's hooked up to 120 volts. And if we clip on an amp meter, we see that it's drawing 8 amps. So what's the power output? Power is voltage times current. So in this case, 120 volts, 8 amps, 960 watts. In this particular case, we'd like to know what kind of current is this device drawing. We know that current is power divided by voltage. So in this particular case, It's 150 watts divided by 120 volts, which gives us 1.25 amps. In this particular case, it wants to know the power, and I don't know the voltage, but I do know the resistance, and I'm able to measure the current. So I'm going to use this equation. Now I've increased the current to 1 amp. Now what's the power? It's 4 times the original power because of this squaring, because of a factor of a square. This is showing how a watt meter works. I have current terminals, and this creates a magnetic field as current's flowing through here. And I have voltage terminals. So I'm looking at the voltage and I'm looking at the current. Each of these create magnetic fields in combination with one another. And so the deflection of this meter has to do with both current and voltage. Here's one hooked up to a circuit. So the reason we have electric circuits is so that something can get done for us so that we don't have to, or so that we're more comfortable. And we're going to use this to convert electrical energy into some other type of energy. I have electrical energy going into this device, and I have light energy coming out. And that's what's intended to happen. But there's also heat that is being created, and that is a conversion of electrical energy to heat that I did not want and cannot use. In fact, I may have to use other forms of energy to get rid of it, like air conditioning. So this is an inefficiency of this device, and it's wasted output and wasted energy cost. Here is the kilowatt meter. I think we talked about this once before. It reads how many kilowatt hours. It's a kilowatt hour meter. Here is a kilowatt hour meter. I think we talked about this earlier before. This is what the power company uses to know how many kilowatts times hours that you're using energy. Inside, we have, similar to the watt meter that we looked at, so we have a current and a voltage winding in the magnetic fields, and both of those will affect this. Here we see how it's connected in your home. We have the high voltage that's coming from our transmission and distribution networks from the power company. We go into our pole transformer to step it down, maybe from 14,400 to 240, and now I have this coming into my meter and then into my load center or fuse box in the home. And here's my available circuit power. Here I have a couple different types of meters. I have a analog and a digital, and reading the digital is pretty straightforward. You simply look at the display here. Reading the analog meter, note that alternating dials going across here also alternate in the direction of rotation, as you see here. This one runs clockwise, but the one adjacent to it runs counterclockwise, and they alternate across. And this is set up like our number system or an odometer. You have a ones, and then you have tens and hundreds. Each one's 10 times the previous one. And the rule of thumb here is that until the dial meter is pointing at a new number, you still read it as the previous number. So here I'm pointed at 2, so it's a 2. But in this case, I have left the 4, but I'm not quite to the 5, so I count it as a 4. And here I've left a 1, but I'm not at the 2, so I count it as a 1, and so on. So in this particular case, I would read this as 57,142 kilowatt hours. If I only have 4 dials, we multiply it by 10. So in this particular case, using that same process, I would come up with this. Now here's an example where I have a 5-dial meter. The power company comes and they read this value and write it down. And then a month, maybe 2 months later, they come and read the meter again and they get this reading. So the question is, how much did I use between this reading and this reading? Well, you take the first reading, take the second reading, and then the difference between the two is the amount that you used, 699 kilowatt hours. Here's a problem where I'd like to know how much a device will cost me to use for a month. In order to do that, I need to know how much I'm being charged for the energy. But this particular device is rated at 4.2 kilowatts. And I'm going to be using this device for 20 hours each month. So I can figure out the cost if I know that the power company charges me 4.5 cents per kilowatt hour. Then I simply do the math. 84 kilowatt hours. Each one of those costs me 4.5 cents per kilowatt, and so it'll cost me $3.78 to run this device for that time interval. So a story I like to tell is the time I went up to Pleasant's power plant, the Will Island power plant. And the reason I went up there was because the college was thinking about developing a degree in power technology. So my job was to go up there and follow the technicians around and see what kind of jobs they were doing, what kind of skills were needed to get a job like that, so that I could come back here and put a program together to teach people those skills. It looked as if there were going to be an opening, a lot of openings at the power plant. So they actually contacted us and said, we're going to have a lot of people retiring and we need some technicians. So if you could help us train them, that'd be good. So yeah, so I go up there and I'm following technicians around. Well, I show up on the first day and I'm always a little bit nervous about going into a new place, especially industrial settings, because there's a lot of new equipment and there's inherent danger in any industrial environment. Plus, I don't want to look stupid because I don't know anything about power plants at this point. And here I'm coming in from the college and I don't want to say something to look stupid or anything like that. So yeah, I'm a little bit nervous about showing up like this, meeting new people. And they said, well, we're going to go up to the control room and we'll kind of hang out there. That'll kind of be our base for all of this. So I'm going to be there 2 or 3 days. I forget how long I was there, maybe 4 days. Anyway, we get on the elevator, we go up 7th floor, where the control house is, and the elevator opens up and I walk out and the floor is grading. It's not a solid floor and I can see all the way down. Now I'm already nervous about being here, being in a industrial setting and meeting new people and all that, but also a little bit afraid of heights. So now I'm already nervous. I walk out of that elevator and I'm standing on this grating to see all the way down. But I don't want to look stupid or scared, so I just kind of suck it up and we go into the control room And once we get in there, there's a solid floor and it's air conditioned and there's people sitting around watching monitors. There's a box of donuts over there. So it's all cool. And after a little bit, I start settling down a little bit. I'm talking and kind of getting to know the people, the crew, and the operations. So over the next few days, that's what I do. I follow technicians around as they're doing their jobs and see exactly what they're doing so I can figure out how to teach other people to do that. But one day up in the control house, they start talking about what goes on there and stories, and they start talking about these stories about accidents, industrial accidents. And I mean, it's like that no matter where you go. And I have my own stories, but they're talking about one day this guy gets his head cut off at work. And I'm kind of like, okay, so maybe this happened, maybe it didn't. But they're telling me about the steam. It's superheated steam that they use to drive the turbines. And it is so superheated that you can't see it when it leaks out. And it's under really high pressure. And they said the only way that you could see it is to take a stick and tie a rag to it, hold it out in front of you, and then when that gets cut off, that rag gets cut off, then you know that's where the leak is. And I'm kind of like, okay, yeah, whatever. And we talk about some other things. It's like, yeah, he got his head cut off from this steam. So I think the next day they're talking about they're going to have to take down one of the boilers. They have two boilers. They have two everything. So if they have to take one generator or boiler down for maintenance or repair, then they're still online generating electricity with the other one. Now that place has huge boilers. In fact, that place is about 15 stories tall, and almost all of that 15 stories is the boiler. At the very bottom floor, underneath the boilers, where the fire is, and they grind the coal up into a real fine dust like graphite. They inject it into it, and it's so fine that that dust ignites almost like a liquid, and that's how they heat. That's how they get this combustion, this big fire. And then inside the boilers where the fire is, they have pipes running with water, and that water in that fire gets super, super hot, and that steam's what they let drive the generator turbines. So they said one day that they're going to take one of those boilers down because there's some water leaking out of the tubes, and I want to go up and take a look inside a boiler. Well, I don't like really to leave the control house because of the whole floor thing, but I say, okay, I'll go with you. And we get up there and we open up that boiler, and this is up probably on like the 11th floor, and it gets hotter and hotter as you go up. Like say it's like 15 stories tall, but every floor you go up is hotter than the one before because of the heat rising and stuff. And so we took the stairs because we're going from the 7th to the 10th or something like that. So it's kind of hot. But anyway, we walk across that graded floor, and I'm trying to be tough about the whole thing, but we get up there to where the boiler access door is, and he opens it up to look in there, and it was pretty awesome. It was like this fire just rolling and boiling over. It was almost black fire, like looking into the sun or something. And he says, "Do you hear that the water coming out of there?" And I did. Said, "So that's what we're going to fix." And he gets a call on his walkie-talkie. He says, "Oh, I got to go take care of this. Can you find your way back to the control house?" And I'm like, "Yeah, I'm not sure if I can." But he says, "Oh, just go around that thing. Just go around the side of that, and you'll see the elevator there at the end." So I hadn't paid much attention about how to get there because I'm concentrating on the floor, right? So he takes off, and I'm there by myself. And I think I can find my way back to the control house. So I start kind of carefully walking back that way. And I kind of see where the elevator, where I think it was. So I'm headed that way. And all of a sudden I hear psst, and I think, I'm going to get my head cut off. And I'm looking around and I don't see any steam, but they said you couldn't see it. He said the only way to find where that leak is to take a rag and tie it to a stick and hold it out in front of you. So I'm looking around for a rag or a stick, and none of that stuff is there. So I'm not exactly sure what to do. I don't really know where he took off. I don't have a walkie-talkie. There's no one to yell for help. I don't want to yell for help if I don't have to. I don't exactly know what to do, but it's a little bit unsettling. So I think about, if this were a leak coming out, there might be a clearing of dirt or something. I should see some signs of where that leak is, a clean spot on the floor or something moving or something, and I don't. So finally I just thought, if I'm going to get my head cut off, it's going to be fast. And I just like ran through there real quick, and nothing happens. I get to the elevator, and I'm pretty excited at this point. So I go down there and get back in the control room, and I'm kind of like, you gotta there's a leak, there's somebody who'll get their head cut off. And they're kind of like, okay, we'll go check it out. So they go up there, and they came back, and it was just like a pneumatic leak, like tire leaking air, something like that. And I kind of overreacted. I figured they were going to rib me about it for a long time, and they didn't, not while I was there. But I'd say maybe they still talk about that at the time the college professor came and got scared from a pneumatic leak, thought he was going to get his head cut off. So that was the time I went to that's my power plant experience.